And here we are for the first video for section 3.2, and we have more derivatives. Derivatives are chapter 3 and chapter 4, so you just need to be ready for derivatives. And then we finally get into what are called integrals, and that's how we end the year. But what we have now is question number 1. We have the function f of x equals x squared plus 2x minus 2, and we want to find what would f prime of 0 be. So the first thing we have to do is to find f prime, and if we remember from last week, what we're going to do is we're going to take this exponent here, at least with this particular problem. Now, a little bit later on, we're not quite ready for the more advanced, so we're going to have to use a formula to find the derivative. It's not near as nice as this shortcut, but eventually we will be able to find the shortcut version of it as well. And so we bring this exponent times the coefficient here, which is 2, and then we're going to take 1 less, so x to the first power is just plain x, plus, okay, this has an exponent of 1, 1 times a coefficient of 2, and this will become x to the 0 or 1, and the derivative of a constant is always 0, so that's where we are at on that. So in other words, all we have to do now is to find what would f prime of 0 be. That would be 2 times 0 plus 2, or 2. So f prime of 0 would equal 2. And that would all be nice, except I wrote the problem down wrong, so we have to make the corrections so that we have no proof of the first mistake of the year. That was a 7. And so that would become this would still become a 2. And this would become a 7, a 7, a 7, and a 7. So f prime of 0 is equal to 7. Now number 2, we have f of x equals 8 over x plus 2. And we want to find what is f prime of 0. Now here's where we're going to have to use the formula. And this formula is the directions for number 4. So I'm not going to rewrite it because you do have those in your notes. But that's where I'm getting this information from. So f prime of x would equal the limit as z approaches x of f of z. Well, f of z is just this with z's instead of x's. So it's going to be 8 over z plus 2 minus f of x. Well, f of x is 8 over x plus 2 all over z minus x. Now we need to get a common denominator here, and so the common denominator would be z plus 2 times x plus 2. And so this will equal the limit as z approaches x of, okay, common denominator up here will be z plus 2, x plus 2. And what we have to do is we have to multiply this 8 by x plus 2. And we have to multiply this 8 by z plus 2. And that still will be all over z minus x. Okay, continuing with some cleaning up. Okay, we will get the limit as z approaches x of 8x plus 16 minus 8z minus 16 all over z plus 2 times x plus 2 all over z minus x. Now if we notice the 16 and the negative 16 will cancel each other out. And then, let's see what we can get from here. Oh, the 8x minus 8z. Let's pull out a negative 8 and see what we get. When we pull out a negative 8, we're left with z minus x. Now there was a reason why I pulled out negative 8 instead of a positive 8, so that I would get it to be z minus x, because look, this z minus x up here will cancel with this z minus x down there. And so then all we're left with is negative 8 over this, the limit as z approaches x of that. So now we should be able to do a substitution, because we no longer have the problem z minus x being in the denominator. That would end up being 0 if we would put in z in for x. So, or x in for z, because we're telling z to go closer to x. So now we can actually do the substitution. And so this is going to give us z is coming closer to x, so we get x plus 2 times x plus 2, all under negative 8. And so this becomes negative 8 over the quantity x plus 2, the quantity squared. And so this is the derivative of 8 over x plus 2. Now, in a little while, we will see a much shorter version. I mean, this is not very much fun, but at the moment, this is where we're at. But we need to remember that we want to know what is f prime of 0. So we're just going to plug in 0 in for x, and so we get negative 8 over 0 plus 2, the quantity squared. That is negative 8 over 2 squared, or 4, which is equal to negative 2. And so the f prime of 0 is negative 2. Okay, example number 3. Example number 3, we are asked to find dv dt. Now we need to remember back to last week, this means the derivative of v with respect to t. That's all this means. So in other words, we might be able to say v prime. However, the problem is we're not in terms of x. So whenever we use prime, most of the time we like to see an x, in terms of x. In this case, it's in terms of t. And v is equal to t plus 4 over t. Now the first thing we're going to do is rewrite this in user-friendly form. In other words, get this t out of the denominator. So that's t plus 4t raised to the negative first power. Now it's in user-friendly form. Now we should be able to find dv dt. dv dt, I'm going to take this with respect to t. So taking the derivative of this, I understand it's a 1. 1 times the 1 is 1. T to the 0 power is 1. So that part becomes 1. Doing the same thing here, take the negative 1 times the 4. That's negative 4. Negative 4, t, I'm going to subtract 1 from negative 1 and get negative 2. Now, we don't like the negative exponent, so I'm going to now rewrite it in the unuser-friendly form, I guess, which is 1 minus 4 over t squared. And that is the derivative, and that is all that we are asked for number 3. Number 4, we now get to use the definition, or the formula there, to figure out what the derivative is. So once again, I'm not going to rewrite it, but we will use the fact that g of x is equal to x over x plus 3. Like I said, just like in number 2, there is an easier way, but you're just not quite ready for that, and you will be ready for that within a couple of weeks. But for right now, we just need to deal with what we've got. So I'm going to take the limit as z approaches x of f of z. Well, that would be z over z plus 3 minus f of x, which is x over x plus 3, all over z minus x. Now if we tried direct substitution, we would let the z be x, and we get x minus x, which is 0. That's no good, so we need to do stuff. First thing I'm going to do, get a common denominator up here. So this will be the limit as z approaches x of, okay, the common denominator will be z plus 3 times x plus 3. So I need to multiply this by x plus 3. So z times x plus 3 minus x, then I have to multiply this thing by z plus 3. So I've got z plus 3, and then this whole thing is still over z minus x. So I can't do the substitution still because I'll still end up with 0 down here. So, well, let's try that one again. The limit as z approaches x of, okay, this becomes zx plus 3z minus xz minus 3x. And for some reason my computer's freezing up at inopportune times. And then this is still z plus 3 times x plus 3. Still all over z minus x. Now, I mess with a couple of these things. For example, zx minus xz cancel each other out. And here I have 3z minus 3x. Well, I'm just going to pull out a 3. Now, once again, why did I pull out 3 rather than negative 3? Because I want z minus x, which is what I'm going to get, exactly, if I pull out a positive 3. So 3 times z minus x, which will now allow me to take z minus x over z minus x and cancel those out. So with that in mind, I'm left with 3 over z plus 3, x plus 3. There's no longer a conflict here, so I should be able to, wherever I see a z, I should be able to put in x. So that's going to become 3 over x plus 3 times x plus 3, which equals 3 over x plus 3, the quantity squared. And there is the derivative of that particular function. Now, for question number 5, we need to really do some thinking, and this is the time when it really starts to get somewhat crazy, or a little bit crazier when we look at graphs. We're given a graph of a function, and we need to choose the answer that represents the graph of its derivative. Well, we need to remember that the graph of a derivative, or the derivative, indicates the slope of the graph at that particular time. So if we looked at, say, I'm going to draw a rough sketch of what's there, just so I can give an idea of where I'm actually looking at on this particular problem. Okay, I'm going to pick this point right here, which may be about negative 15, at x equals negative 15. Well, if I look at this slope, this appears to be about negative 1. The slope of that line there appears to be about negative 1. If I look at negative 10, it appears to be about negative 1. Here at negative 5, it appears to be right at negative 1. But then it starts to curve around so that eventually right here at 0, it actually has a curve or a slope of 0. So it appears, for the most part, it's negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Then it starts going maybe negative 1/2, negative 1/4, and then 0. Then from there, it's going to go 1/4, 1/2, 1, 1, 1, 1, 1, 1. It appears to have a slope of 1 for the most part after that. So what I need to look at is what graphs, pretty much for the entire negative part is negative 1 or so, and it's 0 right at 0, and then it's positive 1 from then on. Well, if we look at, let's try D. D is in dog. D is in dog, all the negatives are positive 1. No, we need it to be negative 1, so that cuts out D. But it does go through 0, 0. C goes through 0, 0, which is what we need. But if we look, it doesn't ever even get to negative 5, so negative 5 might be at, I don't know, negative 40 or so. And here at negative 5, we're saying the slope is about negative 1, so C doesn't work. Likewise, we could use the same argument for B, which would mean A is the only legitimate answer here. A is the one that has negative 1, negative 1, negative 1 for the biggest part of the negative range, and then all of a sudden it hits 0, 0, and then it goes up to about positive 1, which is the slope of this line right here. So I would say A is the correct answer. Now, for question 6, we are asked to find any values of x where f prime is not defined. Now, one of the last questions on the first section was I described how do we know that f prime exists or is defined. That means it is smooth and continuous. So if we look at number 6, is there any place where it doesn't appear to be continuous? Well, to me it looks like it goes on forever. It starts negative, it ends positive, and it's continuous all the way through. We don't have any holes or anything like that. Is it smooth everywhere? Well, it looks smooth in the negative, it looks smooth in the positive. The only problem is right at 0, it does one of these things. It goes down and then immediately creates this point right here. So it is not smooth. So it's not smooth right at that point. In other words, it's not smooth when x equals 0. Therefore, f prime is not defined at x equals 0. Continuing with the same directions, number 7. Number 7, oh, it looks smooth everywhere. You know, it goes to negative infinity and almost to 0, and then it starts back up at 0 and goes to positive infinity. The problem is it's not continuous, and it's our job. Where is it not continuous? Well, it's not continuous when x equals 0, because x equals 0 is an asymptote. So the derivative would not be defined there. And basically, another way to look at it is, what would the slope be right at that point? Or even better yet, going back to number 6, what would the slope be at 0? You know, would it be this slope right here? Or would it be this one right here? Which one? You know, that's why it's not even defined. It's sort of like the limit. You know, if you have two different limits coming from the same place, then the limit doesn't exist. Here, the derivative does not exist because we wouldn't know which side to necessarily pick. That's why it has to be smooth and continuous. Okay, number 8. Number 8 shows a graph, and at x equals negative 1, so we're only interested in that little spot right there. Does it appear to be differentiable? Is it continuous but not differentiable? Or is it neither continuous nor differentiable? So I guess the first question is, since in order to be differentiable, we have to be smooth and continuous, the first question is it continuous at x equals negative 1? It certainly appears continuous to me. I don't see a gap, I don't see a hole. So at least it's continuous. So that takes the last example out. But is it differentiable? In order to be differentiable, not only does it have to be continuous, but it also has to be smooth. And at negative 1, is it smooth? No. It has that point. There's that point on that graph. And so we would have to say, yes, it is continuous, but not differentiable. And it's very important to realize differentiable means the derivative exists. We don't say it's derivatable, you know, it's differentiable. We don't say it's derivatable. Okay, So that's where we're at with that. Example number 9. Over what intervals of x values, if any, does the function y equals x to the fifth over 5 decrease as x increases? Okay, so in other words, let's just do a quick graph of this. Very rough is all that's really necessary here. Y equals x to the fifth over 5. Well, we can rewrite that as y equals 1/5 x to the fifth. Well, x to the fifth is a very sharp, it's going to look very similar to an x cubed, which remember x cubed goes up like this and then up like this. But x to the fifth is going to be even skinnier, and with this 1/5 it flattens it out a little bit, but basically the general shape is going to look like this. It's going to come along here, turn around to create that little S, and we get a curve that looks like this. So now the question becomes, does this function ever decrease? And we look and it's increasing. It's increasing everywhere. So to answer the first question, over what intervals of x values does it decrease? We have to say none. That's question 1, so I'll say part A. Part B says, for what values of x, if any, is y prime negative? Well, once again, y prime means the slope. Well, what's the slope down here? Positive, very steep, positive 40 or something like that maybe. Here it's maybe positive 1. Here it's, 0. Positive 1. Positive 18. Positive 40. Who knows? It's positive. The question is, for what values of x, if any, is y prime negative? Well, that means none. Part C. How are your answers related? Well, basically we know decreasing functions. Decreasing means negative slopes. Decreasing means negative slopes. Negative slopes means negative derivatives. So, decreasing means negative derivatives. In other words, how are they related? They are exactly the same question. Okay, but this is the step. Decreasing function means we have negative slopes. Negative slopes means there's negative derivatives. So, taking this combined with this, the decreasing means negative derivatives. And finally, question number 10. Question number 10. Can a tangent line to a graph intersect the graph at more than one point? Now, if you are listening to this for the very first time, pause this video right now and think about that. Can it intersect a graph at more than one point? And if not, why not? And if so, give an example. Once again, pause it if this is the first time you're listening to this video. So, if you're here, I'm assuming you've either paused it or this is the second time or more that you have heard this. So, what we need to do is we need to come up with a graph. We need to find a tangent line somewhere to a graph that, is it possible to cross it at more than one point? Because we know that tangents are supposed to only touch the graph at one point. Well, what if I take the tangent at that point right there? That's tangent at that point, but look at what happened. It crossed the graph a second time. So here's certainly a case, yes. We need to remember that tangent doesn't mean that it only crosses the graph one time. It's only going to, within a certain range, it will only touch it. Unlike if I try to draw something like about right, say, there. First of all, that's not even a tangent line. That would be called a secant line. So we can't even call that a tangent line, so the whole question needs to be thrown out if we attempt that one. But this one here, we've got a tangent line, but it does cross the graph somewhere else. Okay, so the answer is yes.